Einstein had been giving lectures about his whole curvature theory, right? And he was saying something about curvature, something about curvature. So he was saying that Newton's equation was wrong. He's saying that F equals GMM over R is wrong. And if we can kind of look back and forth between this equation stuff here and this equation here, we should ask ourselves what is missing from this equation. We can sum this up in one single word. So give you a moment to think about that. We look at these equations here, especially this stuff right here, this stuff right here. And then we look at this equation. What's missing? Well, the answer is the partial derivative. Okay, so here we have partial derivatives, or just derivatives in general, and here we have nothing. We have no derivatives. So we're missing partial derivatives. And so that's what Einstein was thinking about. And he was thinking, okay, so how can we represent flat space-time, right? All right, so we have this thing called metric tensor, right? GUV, and we can represent it like this. This is a really basic one. We just have a bunch of zeros, and then we're going to try to figure out what should we plug into these particular numbers, these question marks, to make it completely flat space-time. And we can also represent, like, say, a straight line, right? We can ask ourselves, okay, a straight line is ds squared. Is GUV dxu. This might not make a lot of sense right now, but after we reveal these numbers, this will make more sense. So what are these numbers? Well, they're just ones. Okay, so we're just going to fill this up with ones, and here's a negative one. So that's just going to make things work better with the one. And then we're going to put, basically, you can see how we distribute the ones into time derivatives, and then the three dimensions of space that we have. Okay, so we just have dt squared, and then you can think about this as like the Pythagorean theorem. And what's interesting is that if we set this equal to 0, we'll be able to move this. Oh yeah, this should have a c in it, for the speed of light in here. We'll be able to put this stuff on the left side over here and see basically that the speed of light is going to be traveling in a straight line over here. You can see basically it keeps a speed of light constant. But anyway, so this is how we kind of derive the metric, and we can see that it's a flat space-time here. So now we ask ourselves, okay, so if that was flat, what symbol describes curvature? That's the next question. So on a piece of paper, you might think to yourself, okay, what can we write here? Should we write the Christoffel symbols, curvature? Should we write the stress energy tensor? Should we write the metric tensor? Or should we write the Ricci tensor? So which one of these describes curvature? I'll give you a moment to think about that. And if you got R correct, then that's pretty awesome. So R is how we represent curvature. And so I'm trying to see where my cursor is kind of gone. But anyway, so we have R, which represents curvature, and we could set that equal to R lambda, and then mu lambda v, and so now we actually say, okay, so what is lambda? And this is the next question. So think about this for a second. So what the heck does lambda mean? Basically, what we're doing is we're contracting this stuff. So this is kind of like a shorthand way of writing all of this out. Okay, so we're going to contract all of this stuff into that Ricci tensor. And here we have r to the power of t, r to the power of x. These superscripts are basically the four paths that we can take, but we're going to be changing the derivative in this direction. So like the rate at which time changes, the curvature in space of x and the curvature in that direction. So we're going to kind of be changing differentials in that direction. And then, of course, we're going to be considering the two ingredients. We consider time and space here. And those are kind of one way that we can represent this. So we're basically carrying through this dimension. We're looking at how time changes in the direction of time here, using the ingredients of time and space. And here we're taking the path of the x direction, and we're seeing how these ingredients of time and space affect that. And so we're sort of going down each dimension and seeing how these two ingredients affect curvature in that direction. So that's what we're doing when we contract this all together. So remember that Einstein and Hilbert were working on these equations kind of at the same time, but Einstein was definitely stuck during some of this, and he was working on this for a long time. So he he had to ask his friend Marcel Grossman, and who told him about Riemannian geometry, and that's how we learned about tensor calculus and these Christoffel symbols. So here we have the Christoffel symbols. So this is definitely where Einstein got stuck. And this is kind of some hard looking math, but it's actually not that difficult. So if we look at this, we have a partial derivative here with the lambda. So we're basically taking partial derivatives in the four dimensions there. We have another derivative here, which seems to be space. And so we basically have some derivatives here, and we're taking this gamma symbol. We have a whole bunch of gamma symbols. But if we look at what gamma means, again, we have the superscript of t. So we're going down the path time here. And we're looking at time and space change as we go through the path of time. It's basically what we were talking about just before, but this is how we really represent it in a more official way. We take 1/2 of g. This is an inverse of the metric tensor here, but whatever. These are the two ingredients that we're looking at. So we're looking at time and space, time and space. And so we're just kind of combining um, these ingredients, and we're taking derivatives in terms of time and space. And so we can obviously mix around these ingredients in many different ways, but this is essentially what we're doing. And so if we kind of write all this stuff out, this is basically everything that we need. This is kind of the full expansion. I mean, obviously you could plug everything in, but from here on out, it's all just kind of fractal. It's all just the same things written over and over again with just different symbols here. We're going down different paths. We could switch this for T, X, Y, Z, and here as well, T, X, Y, Z, T, X, Y, Z. So everything just kind of crisscrosses. But this is it. This is kind of what we're doing. This is really interesting here. This is the inverse. We're basically flipping that tensor that we looked at, the 1, 1, 1, 1 thing. We're flipping it around. Here we're just taking the regular old 1, 1, 1, 1, 1, 1, 1. We're looking at the time element. Oh, that was the first corner. You know, here's another corner. Here's another corner. Um, and these are all just partial derivatives. So this is all just a whole bunch of different derivatives. And that's why I'm saying it's not too crazy. We're just taking derivatives in a bunch of different dimensions. Well, now let's ask ourselves, okay, so what are the paths and pairings of time and space? There's actually only two paths that we can take, and that's kind of a trivial question. It's kind of obvious. We have two paths, time and space. But remember I was saying we're changing the rate at which time passes, okay? And that we're changing the curvature of space. So that's kind of what we talk about when we're going down these paths. We're changing the rate at which time passes and the curvature of space. And so what are the different pairings? Well, let's look at the pairings. We have time and time. We have space and time. We have time and space. And we have space and space. So we actually have four pairings and two paths. And so we can line them up like this. And these are kind of the ingredients. So we can take a look at how when we mix time and time together, when we mix space and time together, when we mix time and space together, and we mix purely space together. So obviously this is purely time and this is purely space. So let's consider what that means. Well, it just means that we're looking at how time passes and how the passing of time actually changes the rate at which time passes. So that's kind of weird. It's kind of like this feedback effect here. We can also see how velocity or accelerations change the rate at which both time and space uh, change. And this also just tells you that curvature also changes these things. So these are the three things that actually change these things. Because it's all just about stuff that's changing things, right? Um, time, just the passing of time affects the rate at which time passes and the curvature of space. The velocity at which you're moving at affects your perceived time and the curvature of space around you. And the curvature of space itself determines the rate at which time passes and the curvature of space. So all these things just kind of depend on each other in these crisscrossed ways. And we ask ourselves now, okay, so what is R? Just R, you know, without any subscripts, superscripts, or anything, just plain old R. Um, if you kind of remember anything about scalars, R is a scalar, which means it's just a number. So we can just say it's like kind of like temperature, like 10 degrees, or we could say it's like 10 centimeters. But it's really more like a description of curvature. So we're trying to like measure how something is curved, and we're just going to wrap up that whole R thing that we compressed into that R, mu v. We're going to multiply that by the inverse of the metric tensor. When we do that, remember we're kind of flipping around the metric tensor. When we flip that around and you multiply that by, you basically just get a scalar. So you just get R. So that tells you kind of like this curved uh, ruler, you're basically measuring how much something is curved, and we're just going to put it into a number form and just call it R. So yeah, that's kind of an interesting number. And from here, Hilbert kind of sat around and he was thinking about this for a while. He was a really good mathematician, right? So for him, it was pretty immediate that he was basically able to derive the Hilbert-Einstein action, because this is just basically the standard way to write out the action in a flat spacetime, and then he just added the R in front. Okay, so he just scaled the flat spacetime by R. And what is this? This is a volume integral. So notice that this is a volume integral, kind of a four-dimensional volume integral. And this G here, this would be the determinant of the metric tensor. So what would be the determinant of the metric tensor if in flat spacetime, the 1, 1, 1, 1 thing? What's the determinant of that? It's actually -1, right? Because -1 times 1 times 1 times 1. So we get a -1 from the determinant. And we plug the -1 in here. And when we do that, we just get 1. So basically, we just get a volume that's um, basically a four-dimensional volume that's curved yay much. And that is the Hilbert-Einstein action. So what we need to do now is we need to minimize the action. Oops. We need to minimize the action. Okay, and this has to deal with the Euler-Lagrange equations and stuff. So we're going to set this equal to 0 to basically minimize this, right? And we can ask ourselves, okay, so if we have a straight line and we squiggle that line a little bit, right? Let's say we have to squiggle that line compared to a straight line. How can we minimize the path that we're taking? Well, instead of a squiggled line, it has to be a straight line, right? So essentially what we're trying to do is we're trying to minimize the squiggles in the line that we're trying to take here. And when you do a whole bunch of math and take some derivatives and stuff, you basically get this particular value um, through the Euler-Lagrange equations and doing some setting some stuff equal to 0. So what we're going to do is we have to set this term equal to 0. This is kind of the hardest part of the whole process. But this is how they were able to find the vacuum solution, which is this right here, because we set that term equal to 0. Well, we kind of want to gain an intuitive understanding of these equations, so it kind of helps to remember Huygens' principle, which kind of describes the behavior of waves as they pass through openings, like the wave. I'm sure you've sort of seen this at the pool or something, how the waves kind of have particular behaviors when they kind of go through openings. And considering the gauge transformations, such as like when electrons interact with the photon field and how they sort of twist or rotate the electrons around. So these are some important principles to keep in mind as we look at the vacuum solution. So first of all, what we might notice is that this equation looks very similar to the photon gauge field strength. Um, but if you can't recognize that, no worries. It's kind of some really weird quantum gravity stuff. So let's just kind of try to get more of a real spatial intuitive understanding. And we have this snake here, and we have this baseball. So we can kind of think of this part right here. Remember we contracted all those derivatives into this? This is like a whole bunch of just, they're sort of pointing, they're like heads basically, pointing in a bunch of different directions, like a hydra. 1, 2, 3, 4 heads. Heck, I think they're probably like 16 heads. So, um, so this is like a multiple-headed hydra. And then here, what we have is we're leaving a trail behind us. So that snake is kind of moving forward. And as it's leaving behind a trail, because we're leaving sort of this curved imprint on space-time. It's kind of like if you're walking through the mud, all right? And so that's exactly what this is doing. And if we remember Huygens' principle, like how waves do that, basically this happens in all directions. And if we think about the gauge photon field, well, remember this equation looks like that. So it's the same type of thing that we're sort of rotating stuff as things are interacting. So interesting. Now let's look at this here because this is kind of like a jet stream, right? So you kind of think about that RUV sort of each little piece of the derivative, right? So and it's leaving an imprint on this curved space, and you can sort of read the trajectory as it's going behind you. So this is sort of the second part right here. So those two things kind of combine together to leave the imprint behind, kind of like the jet passing through the sky or something, kind of like snakes leaving their tracks behind. So this is the vacuum solution and how it also might even relate to some quantum gravity stuff. Okay, so now what is the stress energy tensor is our next question, because obviously we don't live in a vacuum, we have stuff in our space, all this stuff right here. And so this might look a little bit scary, but if we look at these P's right here, what do we think that these P's represent? This P right here clearly represents density, right? If we remember some symbols, that's kind of a density symbol. And these guys might right here, maybe it's not so obvious, but it would represent pressure. Okay, so we have density and pressure, and this is essentially um, what the stress energy tensor is trying to represent is how much density is somewhere and how much pressure that's providing in 3 dimensions. So it's the stress energy tensor, and what we're going to do is we're going to set that equal to our equations. So you write all this stuff out. It's pretty simple, I suppose, at this point. We just have k times TUV, some constant, and then we have this. So we're just basically scaling the basic metric tensor. We have all the different derivatives wrapped up, and then we have this scaling R, and we have another scaling constant, and then we have TUV. So just like Hilbert, we could have published this back in 1915 if we kind of really knew some math. It wouldn't have been very difficult to come up with this. So November 20th, 1915, Hilbert did publish a general formula for general relativity, I suppose. Um, so he sends out this publish, and he gets his telegram, right? Well, at this point, Hilbert must have been feeling both excited and nervous. See, right now, he thinks that he might take this discovery away from Einstein, who had the original idea. His hands would have been trembling as he opened up this telegram. Well, it said Einstein presented final field equations November 25th on the Preference Academy. So basically, what happened is a few days later, he got this message that Einstein presented the final field equations November 25th. He was kind of a little bit confused, a little shocked. Well, I suppose he was quite happy because finally Einstein got it. But what did Einstein get that Hilbert didn't get? Well, remember that coefficient k? The coefficient k was actually what Einstein solved for because he realized that it was basically this is Newtonian gravity, and he set this equal to the Newtonian limit and found that you can basically solve for k here and 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 put this into the equations, and suddenly you get general relativity. So he was able to sort of put this in terms of physics, whereas Hilbert was just looking at the math. So it's kind of an interesting story here, but it's all kind of an intuitive understanding and really and a more deeper understanding of how these equations work. This is what David Hilbert said, that every boy in the streets of Göttingen understands more about four-dimensional geometry than Einstein. And yet Einstein did it. So later we had 1916 Schwarzschild solution where he kind of guessed this answer, 1 minus 2 gm over r, and basically did some other guesswork here to find the first solution to Einstein's equations. Just describe this black hole. This is actually the first real evidence for black holes. I don't think they were even discussed much before this, so they didn't really understand what this even meant at the time. They didn't realize, but they sort of started to understand that It meant that there was some sort of extreme curvature happening at this particular radius. It's very interesting. And now we can kind of also gain a more intuitive understanding of the time funnel because we can drop these coins into a spinning thing here. We can look at the top, like top down, and just look down at it. And we'll see the coins just spiraling inwards for some reason. Like if we didn't see the curvature downward, and we just look straight from above, then it would be very strange because we'd be seeing for some reason that these things are just going inward for whatever reason. We wouldn't really know why. And that's the time funnel. You see, there's this extra dimension that's kind of, you can't see it, and it's just sucking things down. And it's basically causing this very strange curvature that, well, there's something there, but we can't see that curvature in our dimension. It's the time dimension. We're, gonna, we're supposed to be the end there, but the idea is that, yeah, this is pretty awesome stuff. Uh, so, hopefully that was pretty fun. Remember that at the M3 archives, we do have the best tools for science progress. And that includes the mechanical formula sheet, the science codex lab manual, the nuclear astrophysics chapter, the quantum physics video series, the study pack, and a bunch of other cool stuff. So make sure to check out physicsformulasheet.com to get the free mechanical physics cheat sheet. That's pretty cool stuff. Thank you all so much for watching.